Good morning. I bet you thought you'd seen the last of math this year. I told you, juniors, that we would look at section 9.2. This is incredibly important. It will make you much more successful as we move on to calculus in the future. So just stay with me, watch it. I'm not going to test you on this. Your grades are done anyway. But this way you've seen this concept and you have a good head start on everyone else. So I'll see you right after the lesson. All right, good morning. Juniors, very exciting. We get to talk about section 9.2, continuity. I know this is exactly what you wanted to do after your culminating activity. And that's great because it's exactly what I wanted to do as well. Let's start by defining continuity. So what is continuity? It sounds like it might be complicated, but just like the limit, I think it's actually much simpler than it seems. And colloquially, continuity is being able to draw a function without lifting your pencil. So a function is continuous if you can keep drawing it, no matter what happens, without picking up your pencil, or in this case, marker. So let's consider the following graph, and then let's think about where the function is continuous and where it is discontinuous, in other words, where it's not continuous. And then we'll look at what this has to do with limits in a second. So let me draw this. So we have all these points and then function connects them. All right, so here's our graph. Where is this function continuous or discontinuous? So starting right here at 0, we're going to use x values to describe this like usual. And that includes 0, right? Because we're starting on 0, so bracket 0. And then I'm continuous all the way down to 1. But at that point, and I know it might be hard to see on this graph, but that's an open circle there. That means that's not a filled in point. So I don't actually go all the way to 1. I go all the way up to 1. So that's parentheses. We're not including it. And then the function kind of jumps from there up to here. And starting here, we're continuous from there all the way over to 2. But again, that's another open circle, so parentheses. And then on the other side of 2, again, not including 2, we're continuing to 3, closed point, and then over to 4, closed point. So we're continuous on all of these intervals. So where is the function discontinuous? In other words, where, when I'm drawing this function, would I have to pick up my pencil? Or my marker in this case. So we're discontinuous at x equals 1 and 2. Let's think about what the limit is doing at each of these points. So if we're thinking about any of these points in between, okay, the limit exists. And if we're thinking about the limit at x equals 3, right, that limit exists. The function is approaching y equals 2 from both sides at 3. Now let's think about the limit at x equals 1. So the limit as x approaches 1 here, we're just going to call this f of x. Well, in order for this limit to exist, the limit to the left and to the right of 1 need to exist. So let's consider the limit as x approaches 1 from the left. And as we approach 1 from the left, we're getting closer to 0. And the limit as x approaches 1 from the right. So we approach 1 from the right, we're approaching 1. So those are not the same value, which means the limit as x approaches 1 of f of x does not exist. And then let's consider the same thing, the limit as x approaches 2 of f of x. Because right now, it might seem like, okay, the limit doesn't exist at x equals 1, and the function is discontinuous at x equals 1. So maybe the limit has something to do with continuity. Okay, a really formal definition of continuity. Well, we need to check, so let's check 2. Again, we need to check to the left and to the right of 2. To the left of 2, the function is approaching 1. To the right of 2, the function is approaching 1. So here, to the left and to the right, those limits are the same. So the limit as x approaches 2 of f of x is 1. And yet, the function is discontinuous. So what is it about the limit, whether it exists or doesn't exist, that has to do with continuity? Okay. Well, if the limit doesn't exist, the function is clearly discontinuous, because that means we're approaching 2 different values from 2 sides of one x value. If the limit exists, that doesn't necessarily mean that our function is continuous, okay? Because what's true at x equals 2? What is f of 2? Is it the limit? What does f of 2 equal? Right? What is the actual function value at x equals 2? It's this point up here. It's 2. And are those the same value? Does the limit equal the function value? In other words, does the value the function is approaching from either side equal what the function actually is at that x value? In this case, no. And our function was discontinuous there as a result. Now, if we think about x equals 3, the limit from both sides is the same, so the limit exists. In this case, it's 2. And what is f of 3? It's also 2. So the limit equals the function value, which means the function was continuous there. We don't end up picking up our pencil. That is the very formal math definition of continuity. So a function is continuous at interior point C of its domain. C is just some point. If the limit as x approaches C of f of x, so the limit equals the function value. For the reasons we just said, that means we won't end up picking up our pencil. We're approaching that value from both sides, and the function equals that value at that point. Okay. But what does it mean for a limit to exist? Okay. Well, the limit as x approaches C from the left has to equal the limit as x approaches C from the right, which should equal the function value. So this right here is our definition of continuity. This is a definition that we will use throughout the entire year in AP Calc. The limit from the left equals the limit from the right equals the function value. I'm going to say that all the time, so get used to it right now. Limit from the left equals the limit from the right equals the function value. Now, before we jump into some examples of how we use this definition to show that a function is continuous or not, I do want to talk about the types of discontinuities. Types of discontinuities. So we have a few types that we classify them, we name them. First, we have what's called a removable discontinuity. So that looks something like this. Suppose we have a function, okay? And then there's an open point in the function, but the function's continuous everywhere else. So there's just a single point. And this point could also have an actual function value somewhere else. Okay? So anytime there's a hole in the function, we call that a removable discontinuity. So holes in functions, those are removable discontinuities. We call it removable because it would be possible to remove the discontinuity if we take that function value and we just fill in the hole. Okay? We would do that with a piecewise function. So it's possible to remove the discontinuity with a piecewise function, hence removable. The second is known as an infinite or asymptotic discontinuity. And as the name suggests, if we have an asymptote, so in this case we had an asymptote right here at x equals 0, then the function is discontinuous because it never actually crosses that vertical asymptote. Okay? And infinite is the other name for it because the function is approaching positive infinity or negative infinity from either side of the asymptote. And then the final type of discontinuity is called a jump discontinuity. So we saw this in our example. The function does something, there's an open point, and then we jump to a different y value where the function continues. So we actually literally jump from one y value to another, creating a discontinuity. So these are the three types of discontinuities. In calc, we talk more about like classifying types of discontinuities, but for now, I mean, it's a pretty straightforward idea. All right, so let's talk about these practice problems. Okay, I'll do a couple right now, and then tomorrow, we'll go through the rest. So I do want you to try once. We'll do at least one together, but then I want you to try the others yourself, and then come back and watch how I finish. So for all of these questions, we are using the same definition. A function is continuous if and only if, and in calc I'll explain more what that phrase means, if and only if. It does have a very particular meaning in logic and mathematics. Sometimes this is abbreviated as IFF. Just again, we like to be a little lazy sometimes. If and only if the limit as x approaches c from the left equals the limit as x approaches c from the right equals the function value. We are using this definition for all of these problems. So let's start with part A. F of x equals, now you'll notice all of these are piecewise functions. Okay, so usually we're dealing with piecewise functions with continuity, because where the pieces split, that's where we could end up with a discontinuity. So this function is 1 when x is less than 0, and the square root of 1 minus x squared when when 0 is less than or equal to x. Okay, now where could this function be discontinuous? It could be discontinuous where the function is split, which happens at x equals 0. So we're going to consider c equals 0. That's where the function could split. And so we need to show, does the limit from the left equal the limit from the right equal the function value? The limit from the left of 0, which piece are we considering there? To the left of 0, that means x is less than 0, so the top piece left of 0. That means the bottom piece, x is greater than or equal to 0, is to the right of 0. So we have the limit as x approaches 0 from the left, and we're looking at the top piece of the function, which is 1. Now we didn't really talk about this, but what happens if there's no place to plug in for x? If there is no x, that just means this constant is the limit value. So this limit equals 1. Okay, what is the limit as x approaches 0 from the right? Well, here we're considering the second piece of the function. And using the same methods that we've always used for evaluating limits, we'll try substitution. Can we plug in 0 for x? Yes, we can. We end up with the square root of 1, which is 1. So far, we've shown that the limit from the left and the right are the same, which means the limit does exist. But is it the same as the function value? Remember, the limit could exist, but the function could still be discontinuous. We need to check. So function value, what is f of 0? So we're looking which piece can we plug into. The bottom piece is for x is greater than or equal to 0. So at 0, we're going to plug into this piece, and we end up with 1. Equal, equal, equal. So f of x is continuous at x equals 0, since the limit as x approaches 0 from the left equals the limit as x approaches 0 from the right, which equals the function value. And these all equal 1. In calculus, we're going to see this much more, how important it is to write out a conclusion or some reasoning behind our answers. This is your first taste of that. So yes, it's absolutely necessary that I wrote this final sentence here, okay? But there we go. And okay, you can use that little symbol we talked about earlier in this year if you'd like. We proved what needed to be proven. All right, so every single one of these problems on this page works this way, okay? I'm going to do the second problem, but why don't you pause, try to work through it yourself, same steps, okay? And then come back and we'll go through it together. So part B, f of x equals, and we have another piecewise function, now, where could this function be discontinuous? Where is the piecewise function split? Well, it's split at x equals 1. So we're going to consider c equals 1 here. And which piece is to the left of 1? That's going to be the top piece here. And then that means the bottom piece is to the right of 1. Okay? Same steps. The limit as x approaches 1 from the left of f of x. That means we're plugging into the top piece. And we plug in 1 for x using our substitution, and we get the square root of 0, which is 0. Limit as x approaches 1 from the right of f of x. Now we're looking at the bottom piece. Plug in 1, also 0. Now we need to consider the function value, f of c, that's f of 1, and we're plugging into this piece, right? This is where x could equal 1, which is 0. So our conclusion, f of x is continuous at x equals 1, since the limit as x approaches 1 from the left of f of x equals the limit as x approaches 1 from the right of f of x equals f of 1, all equals 0. There we go. All right, so that's about it for today. There's nothing else to continuity, okay? Again, this looks super complicated, but I really do hope you're seeing the steps are fairly simple. It's fairly straightforward. Come back tomorrow and we'll do the same thing. I'll go through, the first one, part C, and then D, E, and F are very similar, so you'll work through those and then check your answers with me, okay? Otherwise, let me know if you have any questions, and I'll see you later. All right, so that's it for continuity. Let me know if you need anything. Otherwise, I'll see you tomorrow.